Okay, probability. Now, probability can be a little bit counterintuitive, especially if this is the first time you're seeing it. So, our goal is to start by building the tools for mechanically computing probabilities. Okay, and then we will, interpret these probabilities as we go along. Okay, so hopefully, how to compute them and what they mean will sort of become clear, together as we sort of compute various probabilities for various outcomes. Okay, so now the fundamental thing to remember here is that, probability is relevant when you're doing some experiment and the outcome is unknown, it's uncertain, it's, random in some sense. Okay, so let's consider one such experiment. Okay, so flip 2 coins, okay, and you win if the coins match. And the key here is you're going to flip the coins randomly. Okay, so flip 2 coins randomly, and you win if both match. Okay, now here's an experiment for you to do at home. Repeat this experiment 1,000 times. Okay, repeat 1,000 times. Okay, and see how many times did you win, and see how many times did you win. Okay, repeat 1,000 times and see how many times did you win. And my bet is that you will win approximately 500 times. Okay, approximately 500 times. Okay, now you can do this experiment at home, get a couple of coins and flip them both 1,000 times and see how often they match, and then you count up how many times you won. Now, of course, we're computer scientists, so we can try to do this experiment 1,000 times, in the computer. Okay, and you can do this if you're familiar, or you can look up on the internet. All programming languages, all programming platforms have a tool for randomizing, what's called randomizing. So if you want to pick 2 outcomes, let's say 0 and 1, or heads and tails, you want to pick one of those randomly, okay, i.e. with equal probability, just like what we talked about with 50% chance of picking one and 50% chance of picking the other. So, most programming platforms have a randomizing device, sometimes called RAND. Okay, so you can run this experiment either physically or write a little program to do this and just count up how many times you won. Okay, now what we're going to do is we're going to try to, develop a machinery that would come up with this number approximately 500 times without actually doing the experiment. Okay, and here's the way it goes. Well, the first step, okay, before you sort of invoke the machinery of, computing a probability is to realize that the outcome is random. Okay, so step 1, realize the outcome is random. Okay, and so in this case, that is clearly true. Okay, because who are you going to win or are you going to lose? We don't know until we do the experiment. So it's a random outcome. Okay, and then when you do the experiment, it's not always the case that you will win or always the case that you will lose. Sometimes you might win, the coins will match. Sometimes you might lose, the coins will mismatch. Okay, and so that's what we mean by the outcome of, you realize that the outcome is random / uncertain. Okay, and the outcome of what? The outcome of the experiment that you're trying to do or analyze. The outcome of what? Of an experiment, that you're trying to do or analyze. Okay? Okay. So the next step, okay, when you don't know what the outcome is, but it is certainly possible that you will know all the possible outcomes. Okay, so figure out all the possible outcomes. So in this case, when you toss 2 coins, figure out all the possible outcomes. So first step, second step, figure out all possible outcomes. Okay, now there are many useful sort of aids, tools, devices that you can use to figure out all the possible outcomes. Okay, and this goes back to what we've just been discussing, which is counting. Okay, so figuring out all the possible outcomes is very similar to figuring out the number of possible outcomes, the number of ways that you can toss 2 coins. Okay, and essentially, the way to sort of figure out all the possible outcomes is just an extension of the product rule. So the product rule tells you how to count the possible outcomes, how to figure out all the possible outcomes. Remember that you're doing something and there are, let's say you're choosing a way to do x1, then a way to do x2, then a way to do x3, and so on. And if the number of ways are n1, n2, n3, and so on, then the total number of outcomes is the product. And when we were counting, we were only interested in the total number of outcomes. But now that we're doing probability, we're interested in the actual outcomes. So you can't just tell me that the number of ways of doing, x1, the thing x1 is n1. You have to actually show me those outcomes. Okay? And then for each of the possible outcomes for x1, the number of ways of doing the second thing are n2. Well, you have to show me those outcomes. Okay, and remember when we were doing the shirts and the ties, I represented that on a tree. So a tree is often a very convenient way for sort of figuring out all the possible outcomes. Okay, sometimes we use a grid, sometimes a tree. I mean, there are many sort of aids and tools and devices for figuring out all the possible outcomes, but that's usually the first main step in computing a probability, is to figure out all the possible outcomes. Okay? After you realize that you're analyzing an experiment whose outcome is uncertain, is random. Okay, so in this experiment, just like picking a shirt and then picking my tie, we're flipping 2 coins. Okay, and so it's convenient to sort of represent these outcomes on a tree. Okay, sometimes we call this the outcome tree. Okay, so figure out all possible outcomes, and I'll put in parentheses a very useful aid in figuring out all possible outcomes is what we call the outcome tree. Okay. So you start at the root of a tree, okay, which is, think of that as the beginning of the experiment. And now, what's the first thing you do in this experiment? Well, you toss the first coin, okay, and there are 2 possible outcomes, okay. So the first coin can either be heads or tails. Okay. Now, for each of these possible outcomes, what can happen next? Okay. So if the first coin is heads, you toss the second coin, you flip the second coin, and its outcome can be either heads or tails. Okay, heads or tails. Okay, what about if the first outcome was tails? Same thing. You flip the second coin, and its outcome can be either heads or tails. Okay, and so we call this the tree, for the experiment, or the outcome tree for the experiment. But go think back to the product rule when we talked about counting, and when we were interested in the number of possible outcomes, we just did 2 times 2. So n1, number of possible outcomes for experiment 1. N1 equals 2, and in this case, the number of possible outcomes for experiment 2, for the second flip, after you have done the first flip, okay, is 2. So N2 equals 2, and so the total number of outcomes when we were doing counting, the total number of outcomes is the product gives 2 times 2 equals 4 total outcomes. Okay, and we see them here. So you've got heads, so we'll label that outcome heads. You've got heads, tails, we'll label this outcome heads, tails. You've got tails, heads, we will label this outcome tails, heads. And you've got tails, tails, we will label this outcome tails, tails. Okay. And this method that I'm describing for constructing all the possible outcomes, you can always fall back on this method when things get a little hazy. Okay. Now, and if when we were counting, we were just interested in the number of outcomes, but now that we're doing probability, okay, we list all the outcomes. Okay. Now, it's the tree and the method of getting to these outcomes is not so important. What's important is that we got to these outcomes. Okay. Now, when we talk about probability and sets, what we will say is that for each outcome, you need to assign a probability. Okay. So for each outcome, you need to assign a probability. Okay. So for each outcome, you need to assign a probability. Okay, and once you have assigned probabilities for these outcomes, that's all that matters, and we can run the machinery of probability theory. But now what I'm going to do is I'm going to spend a little bit of time telling you how do we assign probabilities to the outcomes for most of the experiments that we are interested in performing in practice. Okay. Now, in theory, you can assign any probabilities you want here, and you have defined, a mathematical object, which is a set of outcomes with a set of probabilities. But for almost anything we do in practice, there's an associated, sequence of steps that take place. Okay, and in each step, you can represent each step by, a branching of, of a node in a tree. So the root node is the first step, and it branches into the two possible outcomes. Then the second node here is, what happens in the event of a head, you branch off. What happens in the event of a tail, you branch off. So trees are very good ways of representing the sort of sequence of events that can happen in practice, okay, when you run an experiment. Because whatever you do in practice, you have to do it sequentially. Step 1, step 2, step 3, step 4, step 5. And it's ideal to represent that on a tree. Okay, and just like in this case. Okay, and then when you have these kinds of experiments that you do, it's typically the case that each step in your experiment results in partial outcomes. Okay, so you can think of heads as a partial outcome of this experiment, and then when you do the second step, you go heads, heads, and now you've got the full outcome. And you can even assign probabilities to these partial outcomes. Okay, and this is where the mechanical probability comes into play. Okay, so one thing I want to mention before we continue, that you might say, well, you've got heads, tails, so heads, tails, so that's the first coin came up heads, and the second coin came up tails, and then you got tails, heads, and so the first coin came up tails, and the second coin came up heads. And you might say, but aren't these the same outcome? You got one heads and one tails. Well, they are effectively the same outcome if all you care about is the set of, flips. But sometimes you might care about the sequence. So this outcome and this outcome are different outcomes, and that becomes important when it comes time to assign probabilities. Okay, so let's start at the first partial outcome, and we will ask, well, what's the probability of coming to this heads, and what's the probability of coming to this tails? Essentially, we are saying we need to assign a probability to this edge and a probability to this edge. Okay, and the probability to this edge, now it depends on how you flip the coin, and this is where the term randomly comes in. Okay. Now, typically when we say randomly, we mean that each of your choices is equally likely. So in this case, we have, two choices. Okay, so randomly means each choice is equally likely. Okay, and so one thing that you need to know about probabilities, and this is part of the mathematics of our mechanical probability setup, is probabilities add up to 1. So it's 50% chance of rain tomorrow and 50% chance of sun tomorrow. Okay, so 50 plus 50, 100%. So something must happen tomorrow. So when we represent probabilities using sort of percents, or actually we're going to use numbers between 0 and 1, those numbers must add up to 1. Okay. And so since these two outcomes are equally likely, that's what flip a coin randomly means. Okay? And you can think of a coin as a randomizing device that chooses equally likely, that chooses one out of two equally likely outcomes. Okay, and you can think of k-sided dice or k-sided coins, or actually running in your computer, we've got a randomizing device, RAND. Okay, and so if each of these two outcomes are equally likely, and those are the only outcomes that can occur, then their probabilities are 1/2 and 1/2. Okay, because the two probabilities, so you can think of 1/2 as 50%. 50% of the time you get heads, 50% of the time you get tails. 50% is we use 1/2 to represent 50%, 1/2 to represent 50%. 1/2 plus 1/2 is 1. So these are the only two equal numbers that are between 0 and 1 that add up to 1. Okay, and now, so you can interpret this as saying, when I start this experiment, half the time I will go down this branch, half the time I will go down this branch, 50% of the time I will go down this branch, 50%. So with probability 1/2, we go down this branch. With probability 1/2, we go down this branch. Okay, so that's the way this would be read. And we can say that, okay, we've analyzed the first step of the experiment. Now, if this happens, it's the same experiment again with the second coin. So 1/2 of the time will go down this branch, and 1/2 of the time will go down that branch. Because again, we're tossing a coin, a fair coin, randomly. Fair coin randomly means equal probability for both outcomes. And the same thing here. If you had gotten tails, which is half the time, half of that time, so half the time once you're here, half the time you'll go down this branch and flip a second heads, half the time you'll go down this branch and flip a second tails. Okay, now, this is the product rule for computing probabilities. Okay, so if I want to compute the probability of this outcome, now this has to do with conditional probabilities. What we say is that the probability of getting this head, assuming that you have fixed this outcome and gotten here is 1/2. Okay, so the probability to get here is 1/2, and the probability to go from here to here is 1/2. And so we say that the probability to go from the root, the start of the experiment, to this leaf, which is the end of the experiment, is the product of the probabilities for that path that you have to travel. So product rule, computes, so let me write it here. Use product rule to compute probabilities of outcomes. Okay, so for each outcome you need to assign a probability. That's what we're addressing here. So use the product rule to compute the probabilities of outcomes. So the product rule here says 1/2 times 1/2, 1/4. 1/2 times 1/2, 1/4. 1/2 times 1/2, 1/4. 1/2 times 1/2, 1/4. Okay, good. Okay, so I'm just giving you a specific arithmetic, a specific way to compute probabilities for these outcomes. You can't argue with that. It's a way to compute probabilities. The only question is this way of computing these probabilities, does it have any meaning? Does it have any link to reality? Is it useful in any way? Okay, and now, and we will see. So let's now pause a little bit and try to interpret this. Okay, so what this is saying is that, so let's sort of interpret this and sort of try to make sense of it. So what this is saying is that, when you do this experiment, half of the time you will go down this branch, which is you will pick heads. Okay, and then of that half of the time, a half of that will come down this second branch. So a half of the half, results in arriving at this leaf node of your tree, this end of the experiment. Okay. So a half of a half is exactly a half times a half, which is 1/4. That's the sort of intuition behind the product rule. Okay. And what this says is that, if you let's say you flipped 1,000 times. Now we'll give an interpretation of this 1/4. Let's say you flipped 1,000 times. You flipped 1,000 times. How many of those times will go down this branch? Well, half of them. Okay, so I hope you said 500 approximately, because things are random. So approximately 500 will go down this branch, approximately 500 will go down this branch. Okay, and then of these 500, how many go down this branch? 250, because a half of those. And how many will go down this branch? 250. And how many go down this branch? 250. How many go down this branch? Of these 500, half of them, 250. So when you run this experiment 1,000 times, 250 times you will end up here. So 250 times you will end up here, 250 times you will end up here, 250, 250. Okay, nice. Okay, and notice that 250 is 1/4 of 1,000. Okay. And so using this method for computing probabilities gives us the way to sort of interpret these outcome probabilities. So the probability of an outcome, is approximately, well, this is a number that we can compute, but if you did this experiment in practice many times, for example 1,000 times, the probability of this outcome is approximately going to equal, now this is a number, but when you do the experiment, it's approximately going to be equal to the number of times you see the outcome divided by the number of times you run the experiment. Okay, and that is exactly the frequency interpretation of a probability. It says that the probability of some outcome is the frequency of times you will observe that outcome when you do the experiment. And this, of course, assumes the experiment is repeatable. Okay? So we can only do the experiment when the experiment is repeatable, for example, flipping 2 coins. But this probability of an outcome still has that same interpretation, even if the experiment is not repeatable, such as the chance of rain tomorrow is 40%. Okay? So it still has that interpretation, even if the experiment is not repeatable. Okay, so I've sort of illustrated how you get to these outcome probabilities, and we've talked about a little bit about the interpretation of these probabilities. Now let's summarize this into two rules, okay, that end up with, for each outcome you need to assign a probability. Okay, so the first, let's call it step number 3. Okay, is you need to sort of compute probabilities for each partial outcome. Okay, or you need to assign probabilities to each of these edges. So assign probabilities to each edge. Okay, and step 4. For each outcome, you need to assign a probability, i.e., the probability of an outcome is equal to the product of probabilities on the path to the outcome. Okay, so for each outcome you need to assign a probability, and so how do you do that? You take the product of probabilities on the path to the outcome. So the path to this outcome is h, and so the product of those is 1/2 times 1/2, which is 1/4. Okay. So couple of notes, observations. First, the root of this outcome tree is the start of the experiment. Okay. The end of the experiment are always leaves of the outcome tree. Okay. And now I will just mention that it looks like this outcome tree is always branching into 2, okay, and then into 2 here, okay, and then 2 here. So a couple of things that will become clear in some of the examples we do. You don't always have to branch into 2. So this is the case for flipping a coin, where the number of outcomes in each stage of the experiment is 2. Okay, and then you moved from the start of the experiment to heads here, the start of the experiments to tails here. Okay, and you could think of a more complex experiment where if you get heads, flip a coin. If you get tails, roll a die. Okay. If you get heads, flip a coin, that gives you a branching into 2, because the coin can be heads or tails. If you get tails, roll a die, that will give you a branching here into 6, if it's a standard 6-sided die. Okay. And you can think, what would be the edge probabilities in that case? They would all be 1/6. Okay, but let's not get into those complications. I just want to mention that don't get fixated on the specific shape of this outcome tree. Okay, points to note. Okay, the start of the experiment is the root. Every step in the experiment results in a branching from nodes, and the end of an experiment are the leaves, okay, which we call the outcomes. Okay, and now we've assigned probabilities to each edge. Okay, i.e., if so, as an example. Okay, now in theory you could assign probabilities arbitrarily. If the coin was not fair, if it wasn't a random flip of a fair coin, maybe it's a biased coin. So maybe 2/3 of the time it comes up heads, and 1/3 of the time it comes up tail. But randomly. So typically if we choose among our options randomly, random choice among k outcomes means that the probabilities for each of those outcomes, so the probabilities along those edges, is 1/k. Implies edge probability 1/k. Okay? So, okay. So what? Okay, so we've done all this. Fantastic. What the heck? So who cares? Now we've gotten probabilities, okay, and we've gotten to the point where, we've gotten probabilities, and we've gotten to the point where we've even interpreted the probabilities of each outcome. But, we want to know, what are the chances that you will win? Okay, and so that's the next step. You ask a question. So step 5. You ask a question. Okay, so in this case, so you can think of this whole process, steps 1, 2, 3, and 4, as preparation. Okay, you've sort of set up the experiment in this formal way with steps. Step 1, step 2, and so on, and you've identified all your possible outcomes, and now you've assigned outcome probabilities. Now, in theory, we can do probability theory just from here. Okay? But it is helpful to know how we got to our outcomes and what are their probabilities. Okay? And now we're going to ask a question. Okay, so what's the question? Well, you win if both coins match. You win if both coins match. Okay, so when do you win? Okay, so when do you win? Okay, now you ask this question, okay, and so when do you win? That identifies a set of outcomes that correspond to this answer. Okay, that this identifies a set of outcomes. Okay. So in this case, it identifies a set of outcomes that correspond to the answer to this question, which answer the question. Okay. So let's see, what are those outcomes? When do you win? Okay. So you win when both coins match. So when do you win? Let's highlight them. When do you win? Here, both coins match, and here, both coins match. Okay, so that identifies a set of outcomes which sort of answer the question. So it's identified the set of outcomes, HH and TT, along with their outcome probabilities, 1/4, 1/4. Okay. That set of outcomes, and this is a formal definition of what's called an event. An event is any set of outcomes, any subset of all the outcomes. Okay, but we are not interested in just any old event. We are interested in the set of outcomes that answer my question. So this we will call the event that is of interest to us. So this is the event of interest. Okay, so that's step 5. So step 5, we could have equally said, instead of ask a question, which then leads us to the event of interest, we could have just said abstractly, identify the event of interest. Well, it's more interesting. It's sort of more intuitive to approach this from what's the question I'd like to have answered, and okay, for that question, what is the subset of outcomes that answer that question? Okay, and we have identified that here, and then step 6, you answer the following question: what's the probability that this question that you asked is going to occur? So when do you win? You win when this happens. How often do you win? What are the chances that you win? So that's where probability comes in. Okay. So how often do you win? Okay. Effectively, we're saying what's the probability of this event? That's the answer to that question. What is the probability of this event that answers the question? Okay, now formal definition. The probability of that event is just the sum of the outcome probabilities in that event. So we'll say that the probability of the event of interest, the event, script E, is equal to the sum of outcome probabilities, which is equal to 1/4 plus 1/4, which is 1/2. Okay. And that's the end of the calculation. Okay, now let's interpret that. What is it saying? So you can interpret this as saying, what's the probability? How often okay, in terms of frequency, how often does an outcome in my event of interest, which answers the question I was interested in, so how often does an outcome in my event of interest occur? Half the time, 50%. Okay? And so now we can go back and sort of answer the question, if I did it 1,000 times, roughly half of the time, I'm going to get an outcome in my event of interest, which answers the question I'm interested in. And so that's approximately 500, and that's where I got that 500. Okay? And we can look at it also from this perspective. I win in this red box or that red box, and we just analyze that, this red box occurs 250 times, approximately this red box occurs 250 times. That's the frequency interpretation of probability. So in all this happens 500 times. And that's what that probability answers. Okay? So this is, so by the way, this is just a very purely mechanical approach to computing a number. Okay? And that number has an interpretation as, how often does the thing you are interested in occur? Okay? How often does the thing you're interested in occur? What was the thing we were interested in? Winning. When do you win? When the coins match. So how often do the coins match? So let me summarize this entire mechanical procedure, and the fact that it has the interpretation as, how often does if you repeated the experiment, how often will the thing you're interested in occur is what makes probability theory so useful in the real world. It allows us to reason about what will happen in a random probabilistic experiment without actually having to do the experiment 1,000 times. And doing an experiment 1,000 times can either be very costly, time-consuming, or even impossible if we're talking about predicting the weather tomorrow. Okay, so summary. Mechanical approach to computing probabilities. Step 1, you need to sort of have an idea what's the experiment you're doing. Okay, and is the outcome random or uncertain? If yes, then figure out all the possible outcomes. Okay. And the outcome tree, the tree of possible things that can happen in your experiment as the experiment unfolds, is a very useful device for computing all the possible outcomes. Once you have computed all the possible outcomes, you need to assign probabilities to each outcome, and that effectively amounts to, for each outcome, multiply the probabilities in each stage of the experiment, which mechanically becomes multiply the probabilities for each edge in your experiment. That leads to this outcome, which is a leaf of the outcome tree. Okay? So assign the edge probabilities and then multiply edge probabilities to get outcome probabilities. Actually, once we have outcome probabilities, we're done with everything else. Okay? And so sometimes probability theory starts by saying, you have a bunch of outcomes, okay, and each of these outcomes has a probability. Boom, and these probabilities are non-negative and they sum to 1. Boom, done. But that's very hard to get a grip on intuitively. It's more intuitive to think about an experiment that naturally leads to the outcomes, and then the probabilities of those outcomes are sort of are interpretable as how often each of the outcomes occurs, which then leads to this, figure out how often each step of the outcome occurs, okay, and then multiply those. 1/2 of 1/2 give me 1/4, okay? So once we have outcomes and outcome probabilities, we're done with setting up the experiment. We now go and ask a question. What are you interested in? What do you want to know? Okay. And whatever it is that you want to know, you should be able to then sort of massage it into a subset of the outcomes that if one of these outcomes occurs, it more or less answers your question. It satisfies whatever you're interested in. In this case, we're interested in when do we win. We win when the outcome is head-head or tail-tail. Okay. And once you have this event of interest, to compute how often this thing you're interested in occurs, you just add up the event probabilities. That's the 6th step in this mechanical route to computing this number 1/2. And then you interpret this 1/2 as if you were to repeat the experiment, how often would it happen? Okay, so the mechanical approach to computing probabilities. Now let's erase and do lots of examples.